Hi everyone. My name is Zach Carmichael. I'm from the University of Notre Dame, and part of this work was done while I was at the Mitsubishi Electric Research Lab. The title of my talk is Pixel-Grounded Prototypical Part Neural Networks, which has accepted the WACV and the algorithms track, and I'm excited to talk to you all about it today. So I'm going to give you a background about black box classification and interpretability. We're going to get into intrinsically interpretable models, prototype networks, our proposed solution, and we'll get into a little bit of results and conclusions. So black box classification is, of course, where we have some input lead to some output, but there's limited or no decision-making insights. There's a lot of questions that are left unanswered in that process, and there's a regulatory push, including the recent executive order for safe AI, to give some more reasoning and understanding of what's happening there. So in order to achieve this, we also need to acknowledge that that there's a lot of problems when AI is not transparent. It comes to issues with self-driving and uninterpretable results in medical settings. So there's a lot of different ways we can tackle it. One of those ways of adding explainability is post hoc. That's basically where we take a trained model and based on looking at parts of the model or the input and or the output, we come to some explanation using a separate explainer. This is appealing because it provides insights to otherwise inscrutable models without having to retrain or anything. However, post hoc explainers disagree with one another. This is just showing the lack of correlation between different explanation methods that are very popular and the ranking of their features. Furthermore, the fidelity of these explanations is completely unverifiable because we don't actually know what the ground truth is. Post hoc explainers can also be fooled and adversarially or naturally, as well as humans. We can also be fooled by explanations, whether it's an over-reliance with underlying fallacies, or even if it's researcher degrees of freedom. So this is why in this work, not to completely bat aside post hoc explanation, there are some promising avenues, but in general, we are more interested in here in intrinsically interpretable classification, where prediction and explanation are one and the same. This is different from joint explanation and prediction, where you might have a head that does each. And there's a lot of different ways it can be done, whether it's through distillation or additive or neurosymbolic, but we are specifically interested in concept-based intrinsically interpretable modeling. There's a lot of different types of concept-based methods as well, notably concept bottleneck-based. However, that requires strong supervision. And then there's prototype-based, which requires weak supervision or even no supervision. So the first network I'd like to talk about is basically a prototype network, which is based off of a vision autoencoder. When you take those embedded images, you can compare the embeddings to prototypical embeddings of objects, and then simply do a linear combination of similarities between input image embedding and prototype embeddings. And those prototypes can look like these gray cars in the bottom right, and your data looks like these other cars above it, just for a simple cars data set. And a prototype represents different views of a car in this case. To actually visualize those prototypes, we can simply run it through the decoder network of this prototype network. And here we have the prediction being the explanation. This is a type of case-based reasoning, so it's no longer just attribution of features, it's which features are used and how they were used to make the prediction. That is, how each prototype relates to the actual image and what those prototypes correspond to, and the prediction process is somewhat transparent. However, there is no object localization and more complicated data. You don't have any more insights or preciseness, or precision rather. Furthermore, it relies on an autoencoder, and the decoder and encoder networks might not be semantically aligned. That's what led to prototypical part networks being proposed. And this basically goes beyond the object attention, introduces part level attention, and gives explanations the same form of the previous. It also removes the autoencoder. So this network is called ProtoPNet, and it has a couple of stages. We first go through the image embedding stage, where we embed the image with, say, a convolutional neural network. In stage two, we do a prototype similarity comparison of each patch of the embedded image, as well as each prototype that we have, which is class specific. Like we might have, say, 5 to 10 Blue Jay prototypes and 5 to 10 Cardinal prototypes for a bird's classification. Next, we do similarity pooling, which is to assign for each prototype the most similar patch in the input image. So we basically say this corresponds to that with this amount of similarity. This is the support we have for that class being the actual underlying class. And the prediction is simply a linear combination of those scores, where this entire ladder process is understandable by humans. Prototypes are initially random, but they're learned through gradient descent. But since there's no autoencoder, we have to tie it to pixel space. This is done by taking all the training patches of all your training images, embedding them, and then saying, this is most similar to this prototype, so we're going to replace that prototype with this training image patch. So that way the process is invertible. This leads to this embedding, which is now our prototype. So we know what led to the embedding, so we know what it looks like in pixel space. It's a training image. Furthermore, there's a cluster and a separation loss to cluster and push away prototypes of same or different classes, respectively. Now, in order to visualize each prototype, they simply take that similarity map, so that's every patch compared to each prototype, they upsample it to the size of the image and select the top 5% to say this is where this prototype localized to in the input image. There are a lot of derivatives of this approach which try to improve various aspects. However, there is a glaring problem with all of these derivatives and the original method. And that is the pixel space mapping. Again, that's going from the similarity map to the pixel space to identify which pixels were localized to, is ill-formed. It does so, again, by using bicubic interpolation and just taking the top percentile of all pixels. But is it fair to say that just 5% contributed to the similarity score? This ignores the receptive field of the backbone. Furthermore, is it really fair to say that positions in latent feature maps correspond to parts of the input? So this relies on some spatial correlation, which is not really justified in the original paper. So basically, we want to say, and we demonstrate in this paper, that here doesn't correspond to there, and this doesn't correspond to just that. So effectively, what we do is we try to incorporate the receptive field into the model. And in order to do so, we establish what a prototypical part neural network is. It's something where the prototypes must correspond directly to image patches, prototypes must localize to object parts in a principled manner, and case-based reasoning must be describable by simple models. This helps narrow down the literature and all the extensions to identify what the original intent of these methods is. So by design, again, we constrain receptive fields such that we know what each embedded patch corresponds to in the input. It guarantees that part localization. And simply, we just constrain the receptive field of the backbone in order to determine good layers where there's nice and a low Goldilocks zone level of receptive field that determines your localization precision. And while preserving accuracy, we do a proxy task with a subset of ImageNet. And this identifies certain layers and certain architectures, and it's very efficient. To do the new pixel space mapping, we simply assign values in the similarity map in the pixel space according to the receptive fields of each of the similarity scores of each patch. We also replace the classification head with a feature additive or a class-wise additive layer, which removes a lot of coefficients and information that has to be provided to users. To evaluate the interpretability, we evaluate the semantic consistency of prototypes, the semantic robustness of prototypes when noise is added, as well as the relevance ordering test. If I say these pixels were most important, if I start from a random image and add them back, my similarity score for that prototype should go up faster than by adding other pixels. We evaluate on the birds dataset, Cub 200, as well as Stanford cars. And you can see here, briefly, without requiring any bounding box annotations, which other papers have not done yet, which is strange because this is a part localization method, we're able to achieve a better accuracy among methods that don't use bounding boxes, as well as outperform the original ProtoPNet paper across all accuracy and interpretability metrics. And compared across various architectures, we're able to achieve better stability, consistency, and relevance ordering test across all metrics. We'll skip explanations for now, but basically we point out a overlooked issue, we achieve substantial interpretability improvements, and in future work we hope to expand and discover automatic and multiple receptive field selection for our architectures. I just like to mention this can be applied to other applications, including anomaly detection, few-shot learning, conformal prediction, open set prediction. I'd like to thank my collaborators at Merle's I introduced earlier, as well as my advisor at the University of Notre Dame. If you have any questions, please let me know. Here's my email and my website. Thanks so much for listening to my talk.